Hi and welcome to a video on the alternating series test, and this will probably be the first of two videos in this series because we'll talk about the alternating series test, how to show if something converges by this alternating series test, and then we'll also look at how to estimate sums and look at the absolute convergence or conditional convergence probably in a second video. So let's begin talking about these infinite series. And so I can tell if I have an alternating series because of that alternating condition that we put on there. So every other term is going to be negative throughout. These are also seen in geometric series sometimes if our common ratio is negative. We could have also used for some of those the alternating series test to determine if that will converge. So let's just go ahead and get started with this and look through some of these problems, and I'll go through how to actually show that these alternating series will converge or not. So there's two things that you have to show if you are given an alternating infinite series. You have to show that it is a decreasing series, basically. So your n plus 1 term, so your next term, is going to be less than or equal to your current term. And that inequality usually is decently easy to look at. I know some of you just got done with doing the direct comparison test and you may not have liked some of those inequalities, but this inequality shouldn't be too bad to look at. And then you have to look at the limit, and notice there's no alternating condition on that because you're looking for the limit just of that pattern, so to speak, as n approaches infinity. And so I like to start with, if I label this A and B, right, two things that we have to show, and they both have to be true in order for the series to converge. So it converges if. And so I like to do B first. Because we are used to doing limits, we will have to do them quite a bit as well for the ratio test coming up. And so I just like to start with B. If the final term of that series does not look like 0, it doesn't have a chance of converging anyway. So let's go ahead and take a look at some of these examples. So let's test this following series for convergence or divergence. So I can see that it is an alternating series because of that alternating condition that's on there. And so what I'm going to do is actually look for the B part first. So I am going to do the alternating series test. You always want to know which test you're operating under because that will tell you what conditions you have to meet and therefore what conclusion you are coming to. And so I'm going to look at that part B first. So I'm going to say, what is the limit as n approaches infinity of just positive 1 over 3n? You don't need to look at that alternating condition. You can just look at positive 1 over 3n. This is in fact 0. So yep, I would go to part A. And what we're showing in the first part, and I like to think of this series as A sub n, but doesn't necessarily matter what you call it, is that my next term is going to be less than or equal to my current term. And again, you're sort of ignoring that alternating condition because in order to use the alternating series test, you had to have that alternating condition on there. So we recognize it, and now we're moving on. So my n plus 1 term will look like this. Again, you're substituting in n plus 1 for n. So you do need to be careful that you distribute where necessary. So this will turn out to be 1 over 3n plus 3. I can multiply both sides by, the quantity 3n plus 3 times the quantity 3n. And I have 3n is less than or equal to 3n plus 3. Subtract 3n from both sides, and you get a true statement. You cannot just technically stop here. Even though most of us can see that that will be a true statement, you need to go all the way until you have a true statement regardless of your n. And so because both of those are true, I would say this converges by alternating series test, or if you want to abbreviate it, AST. Okay, let's look at a different one. So let's look at this one. Now I have the infinite series, again, going from 1 to infinity, -1 to the n. So there's my alternating condition. So that's what kind of allows me to use this alternating series test. And then my positive or absolute value of this whole series would just be this 3n over natural log of 4n. And again, when I'm in this alternating series test, I am going to try that b part first. So I'm going to look, is my last term, so to speak, 0? So if I look at the limit as n approaches infinity of 3n over natural log of 4n, well, that's actually infinity over infinity. So I'm going to use L'Hopital's rule. Again, this comes up quite a bit in Calc 2. So limit as n approaches infinity, I'll do the ratio of their derivatives. So 3 over the derivative of natural log of 4n would be 4 over 4n. And we can rewrite that. So limit as n approaches infinity. And yes, I understand that this, will reduce. 4 divided by 4 is 1, but I'm just going to leave it for now. And so this will become 12n over 4, or 3n. And if I put infinity in for n, this is infinitely big. It certainly is not 0. And so therefore, this cannot converge. This diverges. And you can say by the alternating series test, but the test that you actually ran on this right now, the alternating series test has the divergence test built in. So I would not be upset if you said divergence test here. If you're in a different course, you can certainly ask your teacher, but the alternating series test, that part B condition or second condition to convergence here, when you're identifying this limit, if it's not 0, that's the same thing really as looking at that divergence test. All right, so that diverges. Okay, so let's keep looking through some of these. So what if I am not given the pattern? Well, certainly we want to write the pattern, so let's figure out what this is. So this is going to be the sum, and I know it's going to go to infinity. I'm assuming I'm going to try to write it with starting at n equals 1, and then 2, and then 3, and then 4, and then 5, etc. If we need to change that or move that around, we certainly can do so. But I like to just at least start with that as kind of a default. All right, so I'm going to deal with my alternating condition first. So I'm going to say this is going to be -1 to the either, we can say -1 to the n, we can say -1 to the n plus 1, we can say -1 to the n minus 1. Those are kind of the three most common. This one means that your n equals 1 is going to be negative. And these both are, your n equals 1 are positive. So when I look here, my n equals 1 is negative, so I want -1 to the n. Okay, that's going to make my first term negative, my second term positive, etc. So that's getting me that alternating piece that I need. And then after it, I'm just going to write what the pattern is of everything else. So now my numerators, and now again, it's important, you're ignoring your negative because you've already taken care of that in each term with that alternating condition of -1 to the n. All right, so then each term, my numerator, 2, 4, 6, 8, 10, that is just doubling my n value. And then in the denominator, I can see a constant increase of 1, 5, 6, 7, 8, 9. And so it'll be 1n plus, and I have to add 4 to get that first one. Okay, so we write the pattern. So now I can start my alternating series test. Again, I have an alternating series. So in terms of When you get to the point where you've learned all your series tests and you just see sort of a series in the wild, if you will, and you need to figure out which test to use, I actually think the alternating series test is one of the most obvious because it has that alternating condition on it of -1 to the n or n plus 1. But that'll make it pretty obvious that at least I know what test to use. I'm going to again start with that second part, which is basically the divergence test. And so I'm looking at what's the limit of that 2n over n plus 4 as n approaches infinity. And you can use L'Hopital's rule. So for some of you that don't want to use your Calc 1 limits, but my Calc 1 limits tell me that that's 2. But if you wanted to use L'Hopital's rule would show you it's 2 as well, because it is infinity over infinity right now. So I'll do the ratio of those derivatives, so 2 over 1, so I get 2. So I can see that this limit is 2. It's not 0, so therefore diverges. And again, you can say you're within the alternating series test, so that is fine. Or you can also look at it as the divergence test being part of the alternating series test, whatever you're more comfortable with. Okay, so here's another one, and I'm sort of just proving my point that I really like to start with when I'm doing this alternating series test, which that's the section we're in, so hopefully that makes sense to you that that's what we're working within. I'm going to start with that part B. So I'm going to say the limit as n approaches infinity of 5n plus 1 over 3n minus 1. And again, this is truly infinity over infinity. L'Hopital's rule could show you, or your Calc 1 limits can tell you that that limit is 5/3, because its horizontal asymptote is at 5/3. That is not 0. So therefore, I don't even have to go through the part A, because if one of the two parts of that alternating series test sort of condition for convergence isn't met, it can't converge. Because think about it, if your last term isn't going down to 0, then it probably isn't a decreasing series either. So, all right, so I know that's not going to be 0, so I would say this one also diverges. Okay. All right, let's look at this number 5, where again I'm still within this, alternating series test here. There's my alternating condition. I have n over the square root of the quantity n cubed plus 2. And again, a lot of people like seeing that n cubed plus 2 to the 1/2, just so they can recognize that as n to the 3/2 if they had to, as a highest powered term. So, yep, the power in the denominator is greater, so my limit as n approaches infinity will be 0. And then I have to show part A, because again, both of the conditions of this alternating series test have to be true in order for this to converge. And so when I'm looking at my a sub n plus 1 being less than or equal to a sub n is just the series that I'm talking about, so that remained unchanged. But instead of n, I was putting in n plus 1. And so you'll see the numerator became n plus 1, and then I cubed n plus 1. So I did have to multiply that all out eventually. I'll show you where that happened. So one thing that you will note is once you multiply both sides by that common denominator, you're going to be here where the hand is showing. And because both sides had 1/2 powers to them, and there was just one term on each side, I went ahead and squared both sides. And so I could then just, like I said, cube out that n plus 1, right? So there's that n cubed plus 3n squared plus 3n plus 3. And then I have to distribute in the n squared. So the right hand side becomes, just quite a few terms, as well as the left-hand side because I had to square the quantity n plus 1 and multiply that by the quantity n cubed plus 2. So then I come up with a fourth degree polynomial. So you can certainly graph this polynomial. You can try substituting in values for n to see if you think this is true. You could try to solve when does this polynomial equal 0. But again, if you look graphically, you'll see that this is a true statement. And again, we're much more concerned with this infinity part of this summation than we are the n equals 1. I can find a sum from 1 to 5. That's not what I'm worried about. I'm worried about the dot, dot, dot. Will that part of it converge or diverge? So even if you had to change your summation to be from 5 to infinity, we're not necessarily worried about the from 1 to 5. I know that that can be a convergent sum. But I'm worried about the infinity part, and that definitely is true as n goes to infinity. That is definitely greater than or equal to 0. All right, and then last but not least here, we'll talk about some inverse trig. So if you have an alternating function that you're dealing with maybe inverse trig or even sometimes trigonometric functions, you may not see that your next term is less than or equal to your current term. So that inequality might be pretty hard to show. And so you might get caught in trying to figure out that inequality when really, if you just start with that limit, oftentimes with trigonometric functions or inverse trig functions, sometimes that limit as n approaches infinity isn't 0 anyway, so you don't have to work that hard and do the inequality. So again, I just looked at limit as n approaches infinity of this inverse tangent. I graphed inverse tangent for you just on a Cartesian plane, and again, I only graphed the part that's in the first quadrant because n is going from 1 to infinity, so I don't have any negative inputs. So I just graphed this first quadrant piece, and I can see that this does level off. Now remember, tangent has a period of pi, so if you graphed y equals tangent x, it always stays between the x values of negative pi over 2 and pi over 2 for its first cycle, and so, or its cycle closest to the origin, if you will, and then it's, of course, cyclic, so it repeats forever. But if I just look at this inverse, it's going to put it on its side. So instead of staying in between x equals pi over 2, this is going to stay in between y equals pi over 2 for the inverse. So my limit is pi over 2, which is definitely not 0. So it does diverge. And I don't have to do the inequality piece because, again, both of those conditions had to be true. The limit has to be 0 and the next term has to be less than or equal to the current term, and those need to be positive terms as well. Okay, so I think that covers the alternating series test. Students typically like the alternating series test. Let me just talk about the remainders and how to estimate some sums here. And so I'll certainly leave this for you. If you would like to pause your screen and read, you can. It talks about, we can find a partial sum of any series, and we can use that as a tool to approximate our total sum. And so we'll talk about the error involved and all of that. Okay, so let me show you an example because I think that it's not going to be as bad as maybe some people might think. So this is, obviously we're still in the alternating series discussion here, but hopefully you can see that alternating condition of that -1 to the n. And now this is over n factorial. And remember, n factorial is n times the quantity 1 less, 1 less, 1 less, all the way down until 4 times 3 times 2 times 1, for example. Right, so 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. All right, so let's at least first show that this series is convergent, because if this series is divergent, it just continues to grow and grow and grow forever. I don't know that we're going to find a good approximation for the sum just using a partial sum. So let's show that this is convergent. So I first started with, again, I'm labeling it part B because oftentimes people list this condition second, but I tend to find it first because if that's not true, then I'm done. But this limit as n approaches infinity of 1 over n factorial is in fact 0, true. And then I just have to show that that next term, if you will, is less than or equal to current term. And again, these terms being positive. Well, of course they're positive because they're 1 over n factorial, and n is starting at 0 and going to infinity. And by the way, 0 factorial, just in case you're concerned, is defined to be 1 because of that multiplicative identity. So I replaced n plus 1 for n. Here's my 1 over n factorial. So I want my next term to be less than or equal to my current term. I multiplied both sides. And then n plus 1 factorial. Well, n plus 1 factorial, if you think of the definition of factorial, it's in product here of this number times 1 less, times 1 less, times 1 less, times 1 less, all the way down to 3 times 2 times 1. So 1 less than n plus 1 is n. And so I can say that this is the same thing as n plus 1 times n factorial. And now I can divide both sides by that n factorial. And so I get 1 is less than or equal to n plus 1. My factorials are now gone, which is nice. It helps me solve. Subtract 1 from both sides. 0 is less than or equal to n, which is absolutely true. N is greater than or equal to 0 if you read that from the n. And that's exactly what my series states in the beginning. So I know it converges by alternating series test, and now I'm ready to find the sum correct to 3 decimal places. So what I want to do is write out what this series is going to actually look like. And I went all the way out to n equals 10. Depending on how accurate you need to be will usually depend on, how many terms do you want to see here. Also, the size of your decimal will depend on obviously how many n's you need. So I just put way more than enough. Okay, so this is what the series looks like in expanded form. That has nothing to do with our summation or our convergence or divergence at this time. All I did was take that series and write it out in expanded form. Okay, so I can find what these values are. Again, people panic when they see 0 factorial, especially when they see it in the denominator. 0 factorial is 1. So that's really 1 over 1 minus 1 over 1. So those are going to add to 0. So I'm going to start with just looking at what are these values as decimals. And when I write them out as decimals, because we're going to be adding 1 decimal and then subtracting another one, adding 1, subtracting 1, right? That's the whole idea of an alternating series, is that one term is positive, the next term will be negative. So if I want this correct to 3 decimal places, I want to look and find the fraction that when I figure out or do the computation to figure out what its decimal value is, where it does not impact my sum to that third decimal. So if you look, 0.5, I need that one. 1/6 is 0.1667, I need that one. 1 over 24 is 0.04167, I need that one because that's impacting that second decimal place. 1 over 120 is 0.0083. That is definitely still impacting my third decimal. 1 over 720, here's where some people stop and I say, well, that 001 is still changing your third decimal, so you need that one. So go one more. 1 over 5040 would be my next term. And when I look at that, it's 0.0001. And even if you rounded that, it would be a 2. That does not round to your third decimal. So if I had 0.0009, I'm going to keep it because technically that 9 rounds my third decimal to a 1. So really, if I was talking about wanting to be completely accurate, I might go ahead and keep that term in there. So for this one though, I have this 0.0001, so I don't need that term, so I don't need 1 over 5,040. I only needed these first 5 terms, okay? And I add those all up, and I find that it's 0.368. This is actually the sum of this infinite series estimated correctly to 3 decimal places. Again, because we're adding a little bit, subtracting a little bit, adding a little bit, subtracting a little bit. And we know that this is a decreasing series, so each next term is going to be smaller than the one that I currently have. That was part of that alternating series test for convergence. I also know that the last term looks like 0, so eventually I'm going to be adding on almost nothing and subtracting almost nothing. But the nice part is with the alternating, you're adding on a little something, but then you're subtracting a little something. And so I can usually find my sum with a decent, accurate estimate within the first 10 terms. Often, I'm not saying always, certainly. So let's just look at one more example of this just so you can get a feel for how it's really working. So if you have, again, this alternating series here because of that alternating condition, -1 to the n is there. So if you look at that series as if it was just the infinite series starting at n equals 0 of 1 over 10 to the n times n factorial, we can show that this is convergent because the limit as n approaches infinity, it actually gets to 0 pretty quickly because you're taking a power of 10 and multiplying it by a factorial. That denominator grows very, very quickly, and then 1 over something real big definitely goes to 0. And then I can show through some computation here or algebraic manipulation that my next term is going to be less than or equal to my current term. So I substitute in n plus 1 for n, and I can then multiply both sides, divide some terms out, and I get n is greater than or equal to -0.9 or 9/10. That is definitely true because n starts at 0 and goes to infinity. So I've showed series convergence by alternating series test. Now I can answer this question. How many terms of the series do we need to add in order to find the sum to an accuracy of where the error is going to be less than, and I've got 1, 2, 3, 4, 5 zeros and then a 5. Okay, so that's what we're looking for. So I'm going to expand this series out, and again, you aren't sure at the time how many terms to write down. So you'll notice my dot, 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 and I tend to want to write down a few more than I think I'll need because then I can always work backwards and find, the next term if I have to. So I started at n equals 0. Don't forget 0 factorial is defined to be 1. 10 to the 0 is also 1, so my first term turns out to be a 1. And then minus 1/10 plus 1 over 200, and then look how fast this denominator is growing. Now I have 6,000, 240,000, 12 million, etc. So it's probably going to grow pretty fast in the denominator, so my decimals are probably going to be very small, very fast. So again, keep this decimal in mind. I want 5 zeros and then a 5. So obviously when I write out this green part, that's what I'm looking for. So I need to keep this 1 minus 0.1 obviously plus 0.005 because that is definitely going to change that 6 decimal. And then 1, 2, 3 zeros, 1, 6, 7, keep it. And then I have 1, 2, 3, 4, 5 zeros and then a 4, 1, 7. So 5 zeros, 4, 1, 7, that is less than 5 zeros with a 5. Again, because 4 is less than 5, right? And all your zeros lined up. And so I don't need that term, right? That is definitely less than my desired accuracy. So it's not going to change my sum by more than this amount. So what you're looking for is you're going to keep any decimal that changes your sum by more than this amount, whether it's adding or subtracting. That's why it has the absolute value of your error here, because that part of it doesn't matter. We recognize that every other term is going to be negative. So I really only needed the first 4 terms, and it was just asking me, how many terms do you need? I only needed 4, right? So we only needed 4 terms to get that sum within our desired level of accuracy. So I hope you found this video on alternating series tests helpful. Thanks for watching. There will be a follow-up video on talking about within the alternating series. We have series that will absolutely converge or conditionally converge, so please look for that. Thanks for watching.